Okay, let's continue. I keep it very short. Oops. I keep it very short with IGA because I want to have more time for the IGA nets and then the caustic design. The way I try to sell to you IGA is as a generalization of the FEM. Yeah, not more spectacular than it is. It's just a generalization of the FEM. And I think, as most of you know it, this is also much easier to kind of understand what IGA is. So 3 blocks. We start with a brief recap of FEM. Yeah, and as a mathematician, please allow me to state very simple things. Linear Poisson with a mixture of Dirichlet-Neumann boundary conditions. Yeah, you all know this weak form. We shift one derivative to the test function. Yeah, so no surprise. This is stiffness matrix. This is the Neumann boundary. This is the load. This is the Neumann boundary condition which we substituted there. The Dirichlet one goes away because we set the test functions equal to 0 on the Dirichlet, all standard, right? So what else? Yeah, what do we do in FEM? We typically just decompose the integral over the entire element over the entire domain into a sum of integrals over domains. And then, at least if we do parametric FEM, we pull them back to the reference element. Why do we do that? Well, because mostly Gauss rules are defined on some reference element, 0 to 1, minus 1 to 1, yeah, to something, yeah, simple shape. And this will be the link to the parameter space in IGA. Yeah, and I'm not sure. So when I learned FEM, push forward, pull back were not so much the terms. It was more, yeah, we are mapping from the reference to the element, to the physical element, and we are mapping back. But to kind of have the analogy, FEM IGA, call this push forward, pull back. I think for quite standard, quite easy to understand. Yeah. Okay. The 2 spaces, the physical one, the element one. Yeah. Just to explain this, mostly the PDE and sometimes the basis functions, but in most cases not, are defined on the physical space. But actually, the entire computation takes place on the element space because, yeah, at least because of the numerical quadrature rules are defined there, and very often also the basis functions. If they are a little bit more evolved, you define them there. Okay. This transformation to and from the element space. I think you have seen this all in FEM classes, but just to recap, yeah, if we have a basis function represented in terms of the physical coordinates, yeah, here we swap in the push forward. Yeah, so with heads, I represent objects living in the reference space without on the physical one. Yeah, if you want to calculate, let's say, derivatives here, derivative with the head means derivative with respect to the reference space variables. Yeah, we get here this term. What is it? It's just the Jacobian. Yeah, if I'm too quick, let me know. But I think this is, if you do FEM, this is kind of the bread and butter of it. Yeah, so you get it here with the transpose. Yeah, we are actually interested in derivatives in the physical space. Yeah, so we want to find technically an expression for this. Yeah, these are all derivatives in the physical space. Yeah, so we are, if it's invertible, we are inverting it, so it ends on that side. I'm now writing it in the opposite way. So now we have a substitute for the gradient in physical space in terms of reference space quantities. Yeah, no magic. Next thing, integration rule also, I think, calculus class. Yeah, if we want to change from one domain to the other, yeah, we are getting here the mapping and then the determinant of the Jacobian of this mapping. And if you piece all together, yeah, so this would be, let's say, for the right-hand side or for the load vector, changing from an integral over a physical element to an integral over the reference element gives us this. Yeah, same at the boundary for the Neumann conditions. And then this looks more ugly than it actually is. Yeah, changing from the physical element to the reference element. Here we have gradients with respect to x. Yeah, this term here from there to there is the counterpart gradient of the test function in the reference coordinate. This is gradient of the solution in the reference coordinate, and then the determinant of the Jacobian. I think, yeah, kind of standard. Okay, then, yeah, we are replacing this one, the test function, by all the basis functions. We are expressing u in terms of its basis, putting it all together, and then we get a linear system. And this is basically copying the quantities from the previous slide. And now, instead of having a phi and a u, here we have the basis. Yeah, and yeah, these coefficients here give us the u vector that we solve for. Okay. One thing, and now I'm coming back to parametrization. What about this f? Yeah, so if f is constant, mathematicians typically say let f be constant. What about a real f? Yeah, that depends on a value, or Neumann conditions that depend on a value. Yeah, so we can either define it in physical space. I mean, that is what I think every, let's say, practitioner would do, define it in the physical space. Then we just have to map it. Yeah, then we just have to map it back to the reference space. Should this be, I know, map it back to the reference space. Or if we have some, let's say, analytic expression, but then per element, we can directly evaluate it. Yeah, so kind of give me the element number and give me, relative to that element, the parameter values I can evaluate f. I'm writing it like this because that will then generalize to the patches in IGA in just a moment. Yeah. Okay, and then last thing, and I agree, this is all, I think, a recap of what you know. Yeah, so now the integral, I've just picked out one of them. Yeah, so the integral is then approximated by, well, approximated, I should say, by a sum. Yeah, weighting coefficients and then sampling points where you sample, or integration points. Think of Newton codes, think of Gauss, Gauss-Lobato, or any other integration. Yeah, and then you approximate it. Okay, now let's, with this quick refresher, transit to IGA. Yeah, so in the previous part, I already asked you to kind of see the mesh as a push forward, yeah, from a parameter space to the physical space. Yeah, and now any field, let's say the field can be the solution, but the field can also be the boundary condition or the load vector. Yeah, any field can be seen as a push forward from A, and ideally the same reference space, to a physical space expressed as this. Yeah. And now let's do a thought experiment. What if we would interpret everything, so the geometry and all the given things? Well, okay, U is not given, U is what we are looking for, but U and all the given things in the finite element method as a kind of parametric model relative to the given basis. Yeah, so don't make the artificial distinction between there's a mesh and there's a solution. It's all the same. It's just a different coefficient. Yeah, but it's all the same relative to the same, or in practice, nested. Yeah, very often you have a finer basis for the solution than for the geometry. Then this basis is nested in that. Yeah, and that is what IGA is about. So we have not two, but we have three spaces. Yeah, this is the patch space. Yeah, these nice B-splines, univariate, bivariate, trivariate that we talked about. This is the physical space. Yeah, where you want to solve your problem. This is, let's say, xi eta. This is xy. And then, and that's why I asked you, what type of functions do we have in a spline space? Piecewise polynomial. Yeah, we cannot integrate over this entire thing because they are not, this is not a polynomial over this entire thing, but only, let's say, they call it sometimes parent element. Yeah, this is an xi I plus 1, eta j plus back again. Yeah. So it's just one extra space just for the integration. Yeah. And then, yeah, again, just to train you in this notation or in this wording, push forward, pull back, and transformation to reference element, you can also say as a push forward or pull back. Yeah, and because you can chain mappings, you can either go from here to there or this way, that way. Yeah, it's all ideally it's all bijective. If not, you made some errors. Okay, so and I'm skipping all the internal details. Yeah, so we start with the geometry modeled as a push forward with the axis. Yeah, then we are decomposing this into patches. There was a very interesting question before. What if we have a hole? I said you can trim or you can, I wiped it. You can decompose it into small patches. Yeah, that's exactly what you do. It's like FEM, but at a coarse or at a macro level. Yeah. Okay. Now the patches become kind of the analog of the elements. So this thing becomes a sum over patches. Yeah. With this pullback operator between it. Then we are decomposing each patch into the many parent elements. That is where we can do integration. Yeah. And then we have, yeah, I abuse the E for element. This is for the integration over parent elements. This is the coarse level subdivision into patches. Yeah. It's not really much more than FEM. Yeah, one sum more or one mapping more. But at some point, if you give up this strict separation, there's a mesh and there's a solution. If you say it's all a mapping from one space to the other, you don't care. Yeah, you can put as many mappings as you wish if they are helpful in between. Yeah, okay. And let's also go over this. This is just a small detail. It's also, yeah, maybe this because I said remember this option too. Yeah, so the way I would see the load vector, and this becomes also helpful for the IGA nets. Say you have a function where you put in P, apologize for overloading P, it's not the polynomial order, it's the patch number, and the coordinates with respect to that patch. Yeah, so you first, this patch, okay, which forward mapping is it? Yeah, okay, then you have identified maybe it's the 10th patch. I have to evaluate the 10th load vector in that coordinate. Yeah, the 10th load vector has this basis decomposition. Yeah, and then for integration, yeah, so these are the coefficients, these are the bases, and in order to integrate this basis, you push it forward or pull it back, depending on from where you look on the parent element. Yeah, so it declare first a, let's say at the first door, a which of my many functions do I have to evaluate, then evaluate it, and for the integration, yeah, put in an intermediate mapping. Okay, now this is, I guess, the most FEM convenient introduction into IGA, because I'm not overselling IGA, just sell it as a generalization of FEM. Good thing is, well, it is, to be more precise, it's Galerkin FEM. Yeah, we started from a weak form. All the theory that works for FEM kind of works there. Well, everything had to be proved, but yeah, most of it has been proved and most of it holds. Yeah, for example, optimal order of convergence, and all these nice things do hold. What unfortunately also holds is the excessive costs of an element-based, so Gauss-based integration. Yeah, and these are some some rough estimates. So approximately one would say, well, P here is again, and sorry for abusing notation, the polynomial order, and D is the spatial dimension. Yeah, so it grows polynomial order to the to the 1 or 2 or 3 if we're in 1 to 3D times the number of nodes. If you do it, let's say, really element-based as I presented it, it scales 3 times worse. Yeah, it's not p to the d, but p to the 3 times d. And many attempts have been made to reduce the cost. I think one of the better ones, I think some years ago it was the best, but now some of the better ones brings it down to p to the d plus 1. Yeah, so we are still a little bit away from the optimum. Bottom line of this is the way you are assembling these matrices, or assembling these matrices, not the way, assembling these matrices is expensive. Yeah, and it is more expensive than in FEM. And to be honest, no one does IGA with first order, because then it is FEM. Yeah, so you typically do it with second, third order. Yeah, so then the costs can be really the bottleneck. Yeah, so the solver is kind of, yeah, okay. It's really building up the matrices. And I'm not sure, have you heard about collocation methods? Who knows collocation methods? Okay, they are somewhat not so popular in FEM, and it has to, is it okay if I say that? Not so popular in FEM.
May I ask you something about
Of course.
the integration? Is it possible to do a patchwise integration?
You mean over the entire patch? Sorry, over the
Yes.
entire patch. It is for sure possible, but one doesn't do it because A, the patch typically has many, many basis functions. And yeah, let me go back here. Yeah, so that means if you would integrate over the entire patch, then maybe the basis function you're interested in is 0 mostly everywhere, only at a small part. Yeah, then you would invest a lot, or you would calculate a lot, or many times 0. And the more mathematical answer is, yeah, so you only know that over a parent element, yeah, so a subset of the patch, the function you want to integrate is a polynomial. Over the entire thing, it's a piecewise polynomial. So maybe with Monte Carlo integration or something like that, you could do, but Gauss or Newton codes, so all that, they are only exact for polynomis and not for piecewise polynomials. Yeah, does it somewhat answer your question? I assume so. Well, maybe to extend on that, in this weighted, quadrature, what that basically does, it evaluates not element by element, but it kind of evaluates everything of a basis function. Yeah, so going back here, if a basis function would be somehow here, then it would be non-zero in these 4 patches. Yeah, a little bit oversimplifying. And then the weighted quadrature kind of sits locally a little here and integrates over all the basis function, over all the elements in which this basis function is not 0 at the same time. But it has some other difficulties. It doesn't give, for example, symmetric mass matrices, because it's constructed like that. So bottom line, Galerkin IGA is nice, but expensive, and the not so popular collocation idea, not so popular in FEM, I would say is becoming more and more popular in IGA. Also because IGA has this higher continuity. So in FEM, one often fights with the C0 continuity, and if one has, let's say, second or third or fourth order derivatives, one needs these auxiliary variables. That kind of is mitigated by IGA. So very few words about collocation and the thing you might not have heard, least squares collocation, or maybe you have. Collocation, if you want to derive it formally as a weak form, comes from the Dirac delta function and a special property called sifting property. Wow, maybe it's just a fancy name for something you know. If you have a function where this function has to be continuous around the point xi, you multiply this. Yeah, so here the delta is the test function. You multiply it by a delta, integrate over it. Yeah, so now this will be solution test function. You integrate over it and want to evaluate it at the point xi. Then this whole integral boils down to evaluate the g, the continuous g, in the point xi. Yeah, same at the boundary. The only requirement is that the function should be continuous. Okay, so we use this sifting to derive another weak form, which is basically the same weak form, but without integration by parts. Yeah, so this is the residual of Poisson, either with a minus or with a plus, doesn't matter. Second derivative of u minus f, weighted by a test function. Now we have to also impose the Neumann condition in a different way, because there is no mechanism that brings in an integral, a boundary integral. We don't do integration by parts. Yeah, so we have to kind of put it in here. Yeah, this is normal derivative minus the value we want to have there, weighted by this. We then, and this is just, yeah, the formality, we kind of define a basis of Dirac delta functions weighted by some coefficients, insert this here, then this becomes this sum, and then we say the coefficients were arbitrary, so we can look at just, yeah, this term here, yeah, kind of a pointwise evaluation of the residual and a pointwise evaluation of the residual at the boundary. Yeah, so giving us, at the end of the day, this linear system. Yeah, so we get k and k sampling points in the interior and n minus k sampling points on the Neumann boundary. Yeah, and then same game as before, we are substituting the u and maybe f or un by the basis expansion, and then get this system. It's in practice much more sparse. Yeah, so I just, many of these terms, yeah, if the basis function is 0 at xk, we don't have to put it here, but just for completeness, basically each row corresponds to, yeah, in the upper part, all the the residual evaluated at one collocation point, and in the lower part, it's the residual at the boundary, at the Neumann boundary, evaluated at the collocation point. Yeah, and to make this work, well, we need a couple of things. First, we need that the basis functions are twice differentiable, and that is one of the things why it's not so popular in FEM, because they're typically not that. Yeah. Another thing that we need is that the number of collocation points, yeah, so the number of rows is equal to the number of basis functions, the number of columns. Otherwise, the matrix is not square, but a rectangular one. Yeah, and then now think, when is a matrix singular? Well, if two columns or rows would be linearly dependent. This is not all sufficient, but it's just, yeah, at least necessary. If you would have two collocation points which are the same, yeah, then you see twice the same row. You could cancel it. Then it's for sure singular. Yeah, so, and yeah, I guess it's easy to see why this is all needed. Then you can solve it. Okay, so just to give you an idea, we need collocation points, and the most natural, or one of the maybe most natural choices, is Greville. Yeah, you use these Greville points. They also exist in 2D, of course. Yeah, you take this degree-dependent average in the one and in the other direction. Yeah, so this would be the Greville points here, and if we map this to this quarter annulus, yeah, then you see where in the quarter annulus the Greville points would come to lie. Okay, this is, yeah, you see here, this will become blue, and then collocation IGA will become red. Let's first look at the left part, that is the solution. Very simple, yeah, just Poisson. Yeah, from the solution, you hardly see any difference. Where you see the difference is in the error. Yeah, so the error, the scale is always the same. The absolute error here for Galerkin is relatively small, whereas For collocation, it is, well, 10 to the minus 5 is also not too bad, but it is measurably larger, let's say. Okay, and if we do mesh convergence analysis, yeah, so now IGA-G stands for the Galerkin, IGA-C stands for collocation. We have to start at cubic because we say we need to do second derivatives. Yeah, we see that the bold lines are always the collocation, the dashed lines are Galerkin. Galerkin has the optimal P+1 convergence behavior. Collocation has some very weird convergence behavior. And if we look, that's not an implementation fault, but that is according to theory. I come back to that. Yeah, so IGA Galerkin, optimal P+1, and the collocation has the odd behavior that if we have an even degree, we have E, H to the P convergence, and if we have an odd one, we have H P minus 1. Yeah, that's why the odds are so odd. Yeah, that's why these two lines are literally or more or less the same. And if you would go 6, 7, 6, 7, then two of them would go like this. Yeah, kind of, it tells you only use every second order. Yeah, comparing the compute time. Yeah, again, same use of colors and line styles. Yeah, basically collocation is much cheaper than even the cheapest Galerkin. Yeah, so that's we don't assemble the matrix. That's where we win. So from the computational aspect, IGA-C is kind of attractive. Now let's think, is there a mechanism to maybe improve it? And I don't mean now to refine. Yeah, refine we can always do, but yeah, so you could also say I do Galerkin and I use a single point quadrature rule. If I have a sixth order polynomial, you will under integrate. Yeah, you kind of make a huge quadrature error. Well, something like this is playing with the control points. Yeah, and instead of using the Greville points, we can also use maybe better points. Again, this is the Greville. Now I use something called clustered superconversion points. Yeah, if I go back and forth, it is reducing. It's still not as good as Galerkin, but it's at least reducing. Yeah, it's not so much big dark red, but less. And if you look to the right, yeah, so the points differ. Yeah, I'm not telling you how to compute these points. These are all in the papers. But at least there are, by playing around with the control, with the collocation points, one can influence the quality of the solution. Again, here, Greville versus so-called clustered superconvergence points. Yeah, so C stands for the normal one, the Greville one, and SC stands for the clustered ones. Gives us some improvement. Okay, and to just give you some background where all this idea comes from and why it is not just trying around and be happy if it gets better and try harder if it doesn't. There's one kind of seminal paper from Hector Gomez and Laura De Laurentiis. They call it variational collocation method. And what they do there is they show that you can get exactly the resolution or the accuracy of a Galerkin FEM with a collocation method if you find the perfect collocation points. And the mathematical basis of that is Cauchy's mean value theorem of integral calculus. So when I had my first calculus lecture, I never thought it would be of so much importance in my life or in research. Yeah, so it's from 18 something or so, which says, this test function has to be all positive and R has to be continuous. Well, and then if we integrate over the product of a test function and R, of course, Cauchy didn't call it test function and R, yeah, that's what I do. Then there exists some tau in the integration domain so that I can pull out this all positive test function here and just have to integrate over that. Okay, which kind of, it's again such of these, there exist, no one tells you how to find it, math theorems. But if you would be able to find these points, you could use them as collocation, because then you can pull out the test function out of this, and you kind of get exactly the integration of what you would get with Galerkin. Yeah, so that was one paper from 16, and then they figured out that they called it Cauchy-Galerkin points because it's based on Cauchy and gives you Galerkin. They figured out that it's not possible to find it in general, and then they suggested some approximate Cauchy-Galerkin points. Yeah, which then this equality becomes an approximation, but it's still okay. And then kind of, yeah, with this, or in this wave of thought, there were papers on superconversion points, and a more recent one on superconversion points clustered together, or a subset of superconversion points, and exactly what we used here.
May I ask you one more thing, if it's possible?
Of course, it's possible.
From what I understand, the collocation is like solving a strong form on specific points, but I'm a bit puzzled when you say variational collocation method, because in my mind it was like two opposite things.
It is, technically it is, and typically the way collocation is introduced, take the strong residual, evaluate it at some points, and hope that it works, or yeah, something like this. If you derive collocation, let's say, all the way starting at a weak form, interpreting the test function as this, yeah, then you really can build up some mathematical theory. Then it is really weak and variational. But yeah, in practice, you typically say, and I fully agree with this, take your strong residual, or take your strong form, evaluate it at the right points, whatever is right, and solve the resulting system. And I'm also not saying, so this variational, where are we? Yeah, this variational collocation method, it was not really practical. So there was no follow-up paper on that. It was more a kind of theoretical bridge between the, let's say, pragmatic collocation and the theoretically sounded or sound Galerkin ones. Yeah, kind of giving you a hint. If you would be able to find the perfect collocation points, which you're not in practice, then you could mimic Galerkin with a collocation approach.
Okay, thank you so much. It was clear.
Do you call this a Vereshchagin rule? Yeah, a Vereshchagin. Okay, this is known in structural mechanics. Yeah. Okay, it's a way to overcome integral of a product of function, that you evaluate one function at a point and integrate the other one. It's called Vereshchagin rule. Yeah. Okay.
Sorry. Yeah. Thanks. Okay, and now we slowly, well, we should also slowly move to the IGA nets. But if we can play with the collocation points to find maybe optimal points, why can't we just pump in more? I mean, machine learning is very often about massive data, yeah? Learn on big data, the more the better. Not always true, but somehow that seems to be the name of the game. Can't we use collocation, but then add more points? Yeah, and well, in IGAC, in the standard collocation, be it with clustered, yeah, so no matter where the collocation points are, there are the requirement that we have as many collocation points as we have unknowns. Otherwise, the matrix is rectangular, so not invertible. Okay, and then there is a paper from Lin et al. From 2020, where they introduced the idea of least squares collocate, or they call it, I think, collocation least squares IGA method, yeah, which basically says, okay, if you want more pages, more collocation points, do it, put in more. They provide, in this paper here, they provide quite difficult to understand proofs under which conditions the method is consistent in conversions, but the bottom line is put at least one collocation point per element. Yeah, kind of, yeah, if you put the Greville points, you have satisfied everything. If you put more, you most likely improve it. That's kind of simplifying things, but that's the primary message here. Yeah, and we did it. Yeah, so C is now Galerkin. Sorry, wrong. C is collocation, I think, with the superconverse. So the best Galerkin, the best collocation we had at hand, and this is least squares. Yeah, so we see least squares is not in the order, so it gives the same order, but it is in absolute terms a little bit better. At least, yeah, not here, but at least here, and here slightly, here slightly. I'm not so much, yeah, focusing on this. We can get better at as collocation. It's more like if I want more points, I can do. Yeah, so I don't have to satisfy this square matrix thing. If I want more points, I make a rectangular matrix, and it still works. And as we see, even better. Yeah, and in terms of compute time, yeah, of course, the more points we have, the more expensive it becomes, but not really radically more expensive. Okay, and you might ask, because I have not shown any of these ugly transformations, is collocation free of transformations? No. They even get more complicated because we have two derivatives. Yeah, so the expressions become more complicated, but use Maple or something like this for it to calculate, let's say, the second derivative of u with respect to x in terms of parametric variables, or yeah, variables. So brief summary of this. I think we looked at a little bit at IGA. We looked at the two weak forms, the one for Galerkin and the one for collocation. We looked at the different flavors of collocation. And basically the last flavor, the least squares one, is the theoretical underpinning of the IGA nets, which we will be talking about now. And let me start with the idea that we have. So I shamelessly stole this from the Siemens blog. What we want is an interactive design through analysis. Yeah, so not you design, someone else and analyzes it, or the other way around, but that you can quick and dirty pre-design things that immediately get some response. Yeah, how will it behave? Not up to the 10th order of accuracy. Yeah, so just qualitatively. Yeah, and I stole this from Microsoft, which is how they think maybe designing cars, and they focus very much on, yeah, the visual aspects, but we of course would be interested in, yeah, what is the aerodynamic property of this, or the structure property of this. Well, I'm more in the CFD part, and the point is it has to be quick, it has to be, let's say, collaborative, and it should be somehow fitting into the, let's say, honest process of doing a finite element or IGA analysis afterwards. Yeah, so spoiler alert, what we do is kind of the same as least squares collocation, but with networks instead of an honest solver. Yeah. So this is basically, I think, what I said. So let's, in view of time, move on. And the thing is, it should be, yeah, basically not one tool for rapid prototyping and another one completely incompatible for the real analysis, but it should be some unified workflow that we can do the one, and let's say upon request, if you are willing to wait more, the other, and it should not leave the mathematical framework. Yeah. And what we do is we use physics-informed machine learning, kind of an operator learning approach in which we replace the one network by a fixed basis, and yeah, IGA, more precisely least squares collocation IGA for the thorough analysis. Yeah, and name of the game is don't leave this IGA or least squares collocation IGA paradigm at all. So let me show you the concepts and a little bit on the costs, and then have some applications. What we do, and maybe you recognize some of the softwares I mentioned in the very first day and in the very first lecture. So Gizmo, that's our IGA package, that, let's say, the honest analysis, which we can always call to give us either training data or to give us the real analysis. And these IGA nets, well, that's the network-based thing. Then that's nice. Both of them are kind of terminal applications. We need some fancy GUI because we really want interactive design. Yeah, so you need something to pull the knobs virtually in a VR setup. Yeah, and we developed, or are developing, I should say, 2 front ends. The one is one on Vue.js. Yeah, so something that directly say covers browsers, iPads or tablets, and VR, XR setups, and another one that's developed by someone in Stephanie's group called Gustav, and I will show you both of them in just a moment. And for that, I have to switch, the screen sharing. And we don't want any monolithic solution, yeah, because that would mean, yeah, if maybe friendship with Vienna stops, then we can't use it anymore. So we wanted some, let's say, no, we'll never stop. We'll never stop, promise. And also not with Surf. Yeah, so we wanted some, let's say, abstraction layer that we say the server or the backend provides some functions to be called, and the front ends provide some functions, or actually call these functions via a WebSocket protocol. And because we want collaborative design, because even possible that someone puts on the VR headset running this and someone else uses the Gustav thing. Yeah, this all is kind of interchangeable. Okay, long story short, our model problem again, Poisson, and I apologize here, I used the delta. This is, yeah, another way of writing the second derivative. And we are encoding, and now I try to change my wording more to the machine learning community. We are encoding everything that we want to input. That is the geometry, that is the right-hand side or the load vector, that is, in this case, Dirichlet boundary conditions. We encode it by either the same or a different basis, and kind of the finite quantity that we feed in are the control points. Yeah, and what we want to get out is, again, a finite quantity, namely the control points of the solution. Okay, so far so good. How does this now fit into the IGA way of thinking? Well, I think exactly that is what IGA does, because what do? We have our geometry, right-hand side vector boundary conditions encoded in the coefficients relative to an a priori decided basis. And then we are computing the solution by inverting. I mean, we never invert, we solve a linear system, but by technically inverting the system matrix and multiplying it with the right-hand side. And what does it mean? Well, the system matrix and the right-hand side depend on the geometry. True, yeah, so that is how we integrate. The right-hand side depends on the right-hand side, also true. And both the system matrix and the right-hand side depend on the boundary condition. What does it mean? The values of the boundary condition really go into the right-hand side. And if you, for example, put ones in the matrix, yeah, so the poorest way of imposing boundary conditions, and you're modifying rows, then in some sense you modify your matrix. That's what I want to indicate here, how, let's say, these objects, yeah, geometry, boundary, load vector, somehow go into the system matrix and the right-hand side vector. Yeah, okay, then we solve it. That means it gives us the coefficients, and then we are done. Yeah, we don't have to solve for every xi value where we want a solution. Remember, in the part on pins, I said, look at this flow field. Yeah, every point in this flow field is a forward evaluation of the pin. if you want really a colorful flow field with millions of pixels, you have a million of forward evaluations of the pin. Yeah. Here we have maybe, I don't know, 100, 200,000 control points, yeah, like in FEM. And then whenever we want to know, and what is the solution, let's say here, yeah, so assume the control points would be here. What is the solution here in the middle? Yeah, we don't have to solve anymore. We just evaluate this here. And I think I have tortured you enough with how to evaluate basis functions efficiently. Yeah, we just evaluate this in that point. So I'm putting this IGA-X thing in this abstract form because we do exactly the same now with IGA nets. Yeah, so this was just what I said already before. We now use all these coefficients as inputs, finite dimensional inputs, finite dimensional outputs to our network. Yeah, and we are just replacing the compute part by a network part. How this network looks internally, we will come to that in just a second. Yeah, that means the geometry encoded in coefficients, the right-hand side, and the boundary encoded in coefficients are inputs, outputs are the use, and we have to train over, guess what? Collocation points. Yeah, we just have to train somewhere. Yeah, we kind of have to mimic this, assemble the matrix A and solve it. Yeah, so we train it for collocation points, Greville points, superconversion points, whatever you want. Okay, and once we have that, that means this is the heavy part. Yeah, so we need forward evaluations, we need forward AD, backward AD, all that stuff. But once the network has been trained, if we have a new configuration, so a new geometry or a new load vector or a new boundary condition, we just query it. Yeah, so we just forward evaluate it. And again, there is not the point where we want to evaluate it. We just say, give us all the coefficients. And from that, we do, yeah, what everyone in FEM at IGA does. We just evaluate in the point, in the concrete point where we want to have the solution. So no surprise that this is maybe the simplest network architecture we could think of. Yeah, we are now trying many different things, but this is the kind of vanilla version of it. Yeah, just a fully connected feed-forward neural network with, as I promised, everything we want to be modifiable from outside as discrete inputs, yeah, in terms of the coefficients, and the solution as output. Yeah, loss function, it's a physics-informed loss function. So a PDE loss and the boundary loss. We are looking if the loss function is not sufficiently small. We continue with the training, otherwise we end the training. Okay, now speaking about the training, how do we train? Okay, first loss function. Yeah. Okay, loss function consists of these two parts, and yeah, nothing surprisingly, right? Yeah, so this is just the collocated residual of the Poisson equation, and this is the collocated residual of the Dirichlet boundary. Yeah, and then here I take k, but it can be more than that. A couple of points in the interior, a couple of points on the boundary. Yeah, and remember, these are, yeah, let's say Greville points or superconversion points. You know where they are, yeah, because they have a nice structure in the parametric domain. Okay, now to the training, what I already wanted to say. Yeah, so we kind of build a database of geometries that we consider relevant for our application. And yeah, this is a little bit yeah, not the weak point, but the point where you have to come with a good knowledge. Yeah, so we are not, of course, we cannot train for a square and then hope that it can predict very well for a I don't know, Christmas tree. Yeah, so, and in practice in engineering, you very often know exactly what typical shapes you have. Yeah, the rotor will never look completely different. It might have a little more spiky or a little broader or a little thicker teeth. yeah, but it will always resemble a rotor or a gear. A gear looks like a gear. It might be a little bit modified in the shape, but it doesn't look like a car. Yeah, so be meaningful, decide what is your geometry database on which you want to train. Same with the right-hand side and the boundary condition. I mean, don't expect to train it for homogeneous Dirichlet conditions and that it can then predict for anything you throw in. Yeah, be reasonable, kind of find a large enough training space so that you are mostly interpolating in it and not extrapolating. Okay, that's the outer loop. Then the inner loop is, yeah, we go over all the collocation points we want in batches. We are training this, yeah. And once it converged, we can query it. And here I'm showing you very, yeah, again, mathematician, a very simple case. We trained on 1, 2, 3, 4 different geometries. Yeah, so different quarter or parts of the annulus. We always have Dirichlet condition 0 here. We have Dirichlet condition 0 and 1 up to 11 here. And then, yeah, it linearly goes down to 0. And as load vector, we tested 0, 1 in discrete steps up to 11. Okay, first test. This is a data that is also seen in the training. Yeah, so F is 5, G is 0, 0 here, and it's, let's say, a known geometry. Okay, this looks qualitatively, and if I haven't said that, I should say, we are not interested in super accurate results. Yeah, this is fast pre-design. We want qualitative results. This looks qualitatively like the right solution. And in fact, we checked it is close to the right solution. Yeah, so now we change same geometry, same load. We change the boundary condition here to 1.4. And well, if we look visually, it gives us really 1.4. So it responds as we would expect, right? Yeah. Now we change more things. This is an unknown geometry. Well, interpolating, right? Yeah. So we are not going beyond 4. It's an unknown right-hand side, 3.3. It's an unknown 2.5 Dirichlet condition here. And it still looks okay, qualitatively okay. And if we now, what do we change? Yeah, we are now changing the load. Yeah, you would, I think, intuitively agree, if we put more load on it, it should kind of deform more. It does. Yeah, so it basically, and we are now currently working on a bigger journal paper with all the conversion studies and comparison to least squares collocation, doing, let's say, all the nitty details. It works. Any questions so far?
So to understand, this is faster than IGA-L because you train a single neural network for a set of problems, where instead with IGA-L you should, for each different boundary condition or load vector, you should solve a linear system. So that's why it's faster. Because otherwise, for a single linear system, for sure it's faster to solve the linear system than to try the train the IGA-Net. Okay, thanks.
And this is exactly so. For a single forward, that was on one of my first slides, I would never see this as a replacement for a single forward. It is, if, yeah, I mean, for this training is maybe a minute or so, but for larger ones, you can train hours. So this hours, there must be a way to compensate. Yeah, if you have thousands of queries, yeah, so my vision is there's really a designer doing this interactively. And then, yeah, basically, if the designer does it an hour, maybe in this hour, there's a million of, yeah, a single node changed is a query. Yeah, there are a million of queries. And then, yeah, this 1 hour upfront training pays off, I hope. There was not anymore. Other questions? Then let me say one thing about the costs. Yeah, so I recognize that I'm permanently talking about costs, computational costs, I mean, of course, and in pins. Yeah, so we looked at that yesterday, how compute intensive it is to evaluate and to train a pin. Yeah, just to recap, what do we do? Already to, let's say, compute the first derivative, we have to differentiate the network maybe in forward mode to get the first derivative. If we want to train, we have to take this and then apply reverse mode AD, yeah, to get the gradient with respect to all the weights so that we can train. Yeah, it's quite heavy. Let's look at the working principle of IGA nets. Yeah, so it's a little bit crowded. I apologize for that. But what do we have? So the network produces the coefficients. Okay. What do we have to do in standard FEM or in standard IGA if you want to compute the derivatives of a function which is represented in terms of coefficients times basis summed over everything? We don't do AD or some fancy stuff. Yeah, we just say the coefficient is a coefficient and the derivative goes to the basis. Yeah, so we leave the coefficient what it is and differentiate the basis. Yeah, so and maybe here from physical to parameter space, the Jacobian, etc., comes in, but this is all standard in FEM. I mean, we do it all the time in FEM. Yeah. Bottom line, if we need second or third derivative, it does not involve a single AD run. Yeah, it's just we are shifting all these derivatives to the test function. That's it. So calculating, let's say, derivatives with respect to physical coordinates, kind of for free. The only time when AD comes into play is when we train. Yeah, I mean, differentiating with respect to the weights. I'm also not a magician. Yeah, so we have to do AD, and I illustrated here in 1D. Yeah, so this is, let's say, the rth derivative of u with respect to some weight. Yeah, we work all this out. This all becomes 0. What survives is this. Okay, what is it? It is, yeah, some derivative with respect to the basis functions, but for that we have this 993 algorithm. Yeah, so this first part here is efficiently computable. And the only thing is we have to differentiate the network output with respect to the weights once. Yeah, so no AD on top of AD on top of AD. Once AD, we're done. And we really see this. I mean, that, yeah, it's not completely free and cheap, but the training, let's say an epoch of the training or a batch of the training goes really quick. Okay, so I think
can I ask a question before you move on?
Of course.
If you go back to the test case that you showed, so it looks like that you're kind of, I don't know if stuck with the original geometry or patches is what it looks like, or like if you're training with that original patch network, if that sticks through all the predictions the network would give.
Yeah, so here the family of geometries was really just 4 parts or 4 instances of an annulus. And well, we could try different things, but I would bet that we are performing worse. What we are now doing is, let's say, generating a database of gears, yeah, and basically this one here, yeah, and then training over a family of gears. And again, yeah, we cannot expect that trained for gears, it then performs for something else very well. I would say really look at what variety in the geometry you need. Put, let's say, all the corner cases you expect the designer or the user will query in your training set and then train for it. But you're right, this is, yeah, if I would now start and ask, how does it perform on a square, for example, or on a, I don't know, even more weird form, it would not perform. Yeah, it would give some weird stuff.
Okay, I think I'm also more asking if you can't really insert more detail in the original mesh that you're starting with, right? You're kind of stuck with the same order of basis functions that you're starting with, or?
Yeah, what we are trying now, but I'm not 100% sure if this works. it should, but yeah, with transfer learning, because mesh refinement is kind of, or is not insertion, is multiplying everything with a rectangular matrix. And that smells like you could put this rectangular matrix up front of your network, and then you only have one layer of weights to retrain. Yeah, so kind of you would start with an already well-trained network, which you then make larger. Yeah, refinement means more inputs. You make larger towards the inputs, and the only layer that is completely uninitialized would be the from the new input layer to the first hidden layer. Was it? I think it's. Yeah, so assume that this is fully trained, and then we want to, let's say, just refine the geometry. Doesn't make sense, but yeah, or let's say we refine everything. Yeah, then we don't have n, but more than n inputs. Yeah, so I would make this the first internal hidden layer. I would put an even larger layer here, but I can reuse all these weights. Yeah, so I don't have to retrain from scratch, but I can kind of only initialize the first layer of weights randomly or somewhat, and then start from there training this network or retraining this network.
Okay, thank you.
May I also ask a question from
Of
online?
course.
I couldn't understand the output part, because I'm assuming if the geometry change, the place that you're trying to get your outputs also change. But what if it doesn't correspond to the same location? So how do you do this post-processing part there?
I guess I understand what you mean. I'm never ever feeding in the value where I want the solution. Yeah, so if you remember what Paris was showing, there was always some either X or Y. Yeah, so the point at which you want a pointwise solution. This is not input in our net. Yeah, so I always want the full control points or U points. Yeah, and it actually doesn't matter. These U points are associated with the underlying geometry. If the geometry changes, yeah, then also where in XY I would draw the U points changes, but not the value. Well, the value, but that is in the nonlinear network.
But U's are your outputs, right? So where you calculate your loss function.
Yeah.
Okay. But
you use my output.
Yeah.
But it's never a U of XY or XYT or XYZ.
Okay.
Yeah, it's really that is actually the thing, which makes it different from deep O nets or all these operator learning things. That I say I don't want a solution in a particular point, and this particular point I feed in. I just want the coefficients. Like in FEM. I mean, in FEM, you're also not asking for solution values. You ask for control points or solution coefficients, and then you can reconstruct your solution in any point in between. Yeah, by just throwing in the right psi eta values and evaluating this.
Yes, I was thinking about the design optimization context. What if, I don't know, your topology changes, or I don't know.
If topology changes, that's another thing. Yeah. No, we are really at the moment one patch. Yeah. So you have your one patch, and you can play with this one patch, not more, not less.
Okay. Thank you so much.
We can couple several patches in the same way as IGA does. But not change the topology.
Okay.
There was one question more in the audience. In 3D, we have the implementation, but so the question was cost 3D, 2D. We have the implementation for the B-splines, but not really tested it in 3D. So it's the evaluation is a little bit more costly, but of course the network becomes much larger, many more parameters to tune. Yeah. So honest answer, I don't. We haven't tested that. Okay, we have this. Yeah, okay, applications. I want to show you two applications. One is the one with, yeah, so what is it, 20 minutes with Surf. Yeah, as I said, this is a in the browser, and I also show you a video from the VR thing that the Surf people did. And then the other is this one, together with Vienna. And for that, I think I have to, okay, maybe let's first start with the VR demo. Yeah, so now this is the interface. Yeah, so you see on the right what you would see with the VR. You are, yeah, you are pulling the knots, and you see on the left that is some other one with an iPad or so connected. You see how the geometry changes, and wow, this is just simple Poisson with Dirichlet condition or 0. Yeah, you see this typical hump in the middle. It somehow reacts to that. Yeah, this was more as a technology preview, how we see it. Yeah, someone designs interactively, and then you see this. Yeah, okay, it's when it gets boring, and luckily it also stops. Where's the? Yeah, I also prepared. Yeah, this is now live. This is running on the Surf machines. So yeah, not the most fancy GUI at the moment, but bear with me. The idea we have while you are creating a session, then you would say, yeah, maybe, yeah, let's take quadratic. We have 5 coefficients in the one direction, 5 in the other. We are initializing it with reveal points. Create. Yeah, okay. So yeah, so you can draw it, then you can modify things. Then yeah, coloring. So here it looks again, auto evaluate. Yeah, so this is now you would change it. You can also rotate things. Yeah, so kind of interactive, yeah, as interactive as this proof of concept can be. I could also connect with my iPad to the same session and then could interactively do it. Yeah, that's a little bit how we see it. It's of course not Rhino 3.0 or so. Yeah, but it's a first attempt. Yeah, proof of concept, what we have in mind, and this coupled then with the VR is a little bit where it should go. And then yeah, if you would say, is it in here already? Yeah, maybe refine it. Okay, then you get a finer mesh. Yeah, so the basic features of a first year's cut geometry modeler and analysis tool we have in there. Well, yeah, and I think, let me try to switch laptop. Okay, yeah, so this is the tool that TU Vienna has been developing there. Another feature, because this was all geometry modeling, but not the right-hand side. Yeah. So what I can also do here is, yeah, of course, model the geometry, but I can also modify, let's say, the boundary conditions. Yeah, so what it means, here I have visually modified the boundary conditions. They were all 0. Now I make this one, yeah, something like 1 or so, and I see that it really changes. Yeah, so the boundary is not purple anymore, but it gets what is it, yellow. Yeah, so this is, we really want it visual, and I think this is more for educational purposes, that you, let's say, have a couple of trained models, Poisson, Stokes, maybe Navier-Stokes, and then let students work on that, like, yeah, explore what happens if you change the boundary value, the geometry, etc., and then get a quick response. Whereas the other is more meant for, let's say, real designers. But yeah, as you see, we are not there yet, just a proof of concept. Any questions on that? So if you want, the link is also on the website. So this is pip install Eigen, Feigen, not Eigen, Feigen. Okay, how do I share screen here? Yeah, so this is really pip install Feigen, and then yeah, running this one-liner, you get this thing to play with. And here, this is visualization.surf.nl/IGA-net. Maybe don't try it all at the same time. Yeah, we didn't do brute force tests at the moment. Yeah, it's a prototype. Yeah, please don't break it. Or if you break it, let me know. Then we can restart it. Okay. Any questions on that?
You train your model with a specific node vector, and then you change it so that you can have more configurations of the geometry. Does it still hold, or do you need to retrain it? Okay.
So that's what I said. If you maybe one refinement and then you can retrain it, you don't have to start from scratch. We also thought about that. Our answer to that is we kind of train a huge database of these. I mean, this is per patch. Yeah? We train a huge database of different polynomial orders, etc. And then, like in Rhino or so, yeah, instead of saying I want, let's say, a square, or I want a I don't know, cylinder, you would say I want a patch with this configuration for Poisson. Okay, and if you want, instead of quadratic, cubic, you have to take a different primitive. Yeah, you have to select a different one. And that's a little bit how we see this to be deployed. And of course, this training, it might take a month, but yeah, if you do this once and then can sell it, not sell it commercially, but sell it to your customer, give it to the user, I think then it's still valid. And well, you can also combine different patches, let's say, of different, well, they have to be compatible at the interfaces, but let's say a 2x3 coupled with a 3x4, for example, you can piece together. And what we are also working on, but this is really just conceptually there, that we have one patch, honest IGA with Gizmo, the next patch, learning-based. Yeah, because it is in the IGA paradigm, it is just another way of producing the same output. Other questions? So if not, I would have one more thing. This caustic design has nothing to do with IGA, and it's a completely independent development, but I like it. I think it's cool. And I think the message is, when you think physics-informed machine learning, don't always think about PDEs, think broader. Yeah. So 2 small parts, and then we are ready for lunch. Caustics, caustic design, and then concepts and some very early results. So what caustics are, I already illustrated that yesterday with this bottle, which is still here, and light. Yeah, it gives you these crazy weird patterns. If light shines through, yeah, this is so EPFL has a big research group doing parts of or working on this. So here in front you see maybe a little bit blurred the lens. Yeah, from here would come the light, and then it is projecting this pattern there. And I said to you, well, where do you use it? High-priced sports cars. You want to be cool, you buy that. Yeah, then they project the label of your choice there, or more serious. And I didn't know it before I talked to our optics group. Yeah. Street lighting. Yeah, you think, what can you, especially after yesterday, since we know that this city was one of the first in Europe to be street lighted, you think, what can you improve there? It either works or doesn't. No, what they do, what they are seriously looking, that you have an, let's say, uniform one. Yeah, so if you just have lights, then it is bright, really there, and it gets darker. Yeah, you kind of get a zebra pattern. This is not really what you want. Yeah, so you want something that is kind of equally bright everywhere. That means here you somehow have to filter away, or well, not away, then you would waste energy, but you have somehow to bend the light that not so much is going like this, but more is going, yeah, into this direction. Yeah, so it seems to be a market for. Okay, so no, yeah. The setup. So now this was caustic. Now we come to caustic design. The setup that we looked at is very simple. Again, academic. We have a source where the light comes from. We have a target plane. Think of it as the street. Yeah, where we want a specific pattern, or more correctly, we want a target light intensity distribution. Yeah, it's not really pattern, but intensity distribution. Yeah, and then we have two lenses, which we model as freeform surfaces. Yeah, normally lenses are kind of, yeah, have a conic shape, yeah, or so. We really model it with B-splines. Yeah, that is, I mean, I like B-splines, whatever. Yeah, whatever doesn't reject it, I try to treat with B-splines. So we try to model the surface, the front lens and the rear lens with B-splines. Yeah, okay, and then the goal is, yeah, given a desired light pattern here, or target light intensity distribution, model or change the surface, optimize the surface so that this light source produces it. Okay, and the general idea, I spare all the details because that would require a crash course on optics. Yeah, so we are defining the locations. That is basically, yeah, the distances from here. Yeah, how far away is the first lens, the second lens, the target plane. These are the D1, D2, D0, D1, D2. Also the type. Yeah, you can have point versus extended light. We made it the simplest, 0.1. Yeah. Then we want to define the shape of the front and the rear lenses by modifying the B-spline coefficients. Then we want to calculate, kind of simulate the resulting light intensity by ray tracing. Who knows what ray tracing is? Yeah. Ray tracing basically means you start somewhere at the source, you shoot a ray virtually, and then, yeah, if it goes through some lens and would reflect or bend, you simulate that. Yeah, how kind of what you would experience if you were the ray. That's what it is. But I have a slide on that. Yeah, then we kind of calculate the error in quotes, because, yeah, how do you calculate errors between density distributions? We also tried something with Wasserstein distance, but I spare you all these details. Yeah, we kind of compute how good is what we produce against what we want to have. Yeah, and then comes the auto optimization loop. We update the control points of the B-splines and repeat steps 2 to 5. Yeah, and now this is what I want to yeah, kind of message. if we see this ray tracer as the physics model, basically it is, yeah, it does what light in physics does. It is our physics model. If we would put that as the physics model in the loss function, yeah, we use the A and N to predict the B-splines like in IGA nets. What do we have to do? So what is the crucial ingredient or the crucial requirement on the ray tracer? It must be differentiable. And if you look in all these computer graphics ray tracers, they are super fast. They are really optimized to the max, but most of them are not differentiable. And there is one, Mitsuba, and Mitsuba 3 is open source. It's coming also from EPFL, and they can do forward and backwards. Yeah, so kind of differentiable ray tracing. This is just a simple illustration. If you would have, and this is a point source. Yeah, so light is coming from a point. Here, the refraction index from light to from air to lens changes. So there is some change in the ray, and then going through the front or rear lens, yeah, another change, and then it would end up there. This is what a ray tracer calculates, yeah, and the same here with let's say parallel light beams, yeah. Mitsuba is a very handy tool that allows us to not just do these forward calculations, but also the backward ones, yeah. So to really differentiate each single ray with respect to whatever are the weights of the network. Yeah, and these are the two target light intensity patterns. Well, the right one, a faceted ball, the left one, the logo of TU Delft, so the flame. Yeah, it was a master project, so we had to do something iconic, sorry. Yeah. Yeah, because neither Audi nor BMW wanted to sponsor us, so we had to, not yet. And this is really the result. Yeah, again, target and yeah, target here, and this is what we produce. So you see, it's not perfectly white, yeah. So there are some artifacts in it, but you can already recognize, yeah, the structure, especially here. I think, I mean, I like this. So it is faceted, and you really see these facets there. Now you might ask, what does magnification 135 mean? It kind of means the distance, yeah. So this is the lens, and this is where the plane is, yeah. So if, and of course, yeah, if let's say the plane is further away, we need a different lens, yeah. So a lens is really designed for a fixed distance between source and lens and target plane. Yeah, so that is what the magnification means, and this also illustrates, I think, a little bit, let's say, how these, yeah, what the ray tracer basically does. Then, and we are really coming to an end, both in terms of slides and in terms of time. We thought, can we do better? Yes, and THB splines should allow us to, yeah, more fine-grained, in a more fine-grained way, modulate the surface of the lens. Yeah, so this would be, let's say, rear or front, doesn't matter. And this is an illustration. So we would start with a regular tensor product B-spline, and then somehow figure out, well, here we need some more refinement, yeah, and have these three levels of coarse, medium, fine B-splines. Okay, and you recognize this figure or this image? Yeah, in the Mauritshuis, so very famous painting in the Netherlands. I was told you must not even use it in a publication without asking Mauritshuis if you can. So we did. This is now, we have a, yeah, in this year, this is a preprint, which is there. By the way, the other thing this year is available as a, should show, as a paper, which is out since yesterday. So really recent results, and this preprint you can download, and we are waiting for the reviews. What we do here is we start, yeah, so this is our target light distribution. We start with this very coarse and tensor product structure. It gives you already the, let's say, the contours, but not really recognizable the young lady. Yeah, and then we are, yeah, this is kind of we the training. Yeah, and at some point we decide, okay, now we switch to a locally refined THB version. Yeah, and what we also do that's a little bit yeah, hand wavy, we are modifying the learning parameter by hand at the moment. We have not found a better way yet. Yeah, so this would be 1 level refinement, 2, 3, 4, etc. And then if you compare, this is now after 6 levels of refinement. I think, what is it? 1, 2, 3, 4, 5. 5 levels of refinement. The loss goes down, yeah, quite significantly, but more impressive, yeah.
Excuse me?
Yes.
Can I ask a question? Yes,
Of
I have a
course.
question about the neural network. It's a feed-forward neural network.
Yeah,
How does it look like?
It's a standard feed-forward neural network without any fancy stuff.
Okay. And just changing the loss function with informing with physics, let's say.
Exactly. So kind of remove the differentiate, say take pin, and instead of computing the derivative with respect to x of the network, we are differentiating the ray tracer with respect to all the weights. And yeah, there's some tiny detail. We are not comparing pixels. Yeah, it's not target pixel minus produced pixel. Yeah, we do some more fancy stuff like Wasserschein distance or these things. So there is some more math involved, but I wanted also, in view of time, spare you with these details. It's more you can replace a PDE physics model by whatever physics, or by at least this physics model.
Okay, thank you.
And then let me conclude the sense that I was about to say here. Yeah, so this is the result that we get. Yeah, I think it looks pretty nice. And this, yeah, so light tools is a really commercially productively used, yeah, lens design toolkit. Yeah, that's really used by Philips and others. And I would say we are not that bad compared to what they do. So, and with this, I yeah, kind of wanted to end the talk or end the lectures, just showing you that well, if you take this idea of physics-informed machine learning and throw out the things that you typically have in and replace it by, yeah, some maybe more exotic physics, maybe some more exotic way of modeling and of optimizing, you can get also such fancy things. Thanks. And if you have questions, let me know, please.